Okay, so I'm going to talk about a graphical model I've developed for doing natural language parsing. But I wanted to give you a quick list of what I'm not talking about. I've also worked on spoken language understanding, have a project currently for dialogue systems, also learning dialogue management policies, combining supervised and reinforcement learning, a bit on data-defined kernels, some earlier work on text mining. So before I present the talk, I wanted to give you a kind of historical perspective on my work on using hidden variables in parsing. I did some earlier work on neural network parsing, looking at the what kind of neural network architecture you needed to capture the generalizations appropriate for parsing. That didn't actually use hidden variables, but when I applied those ideas to a learning-based architecture, here did use hidden variables, and that and this later work is still the only really successful application of neural networks to natural language parsing. Okay, a few years later, I applied it to this benchmark Wall Street Journal Penn Tree Bank data set and got state-of-the-art results with a generative model. Then I did a discriminative.
Is the mic on? Their mic's off. No, they're saying our mic is off. Just unmute.
Do I need to just?
There you go. Thank you.
Okay. So, right, so then I applied a discriminative training method and got, this is still one of the best parsing results on the benchmark task. Done some work on data-defined kernels derived from this model, but that's mostly the work of Ivan Titov, so I won't talk about it here. And most recently, the work I'll be focusing on here, which is formalizing what the neural network is doing in terms of a latent variable model, a graphical model with latent variables. So the talk I'll be giving is actually starting from here and moving backwards, but you see that I've been working on this stuff for a long time. Okay, so I'll start with a brief introduction, then talk about the graphical model, how apply it to parsing, and particularly how to approximate inference in the model, results, and then some further discussion of previous models. So as anybody who's worked on statistical models knows, one of the most important features is choosing the set of features you're going to condition your probabilities on. Usually that's done by hand, but we would like to be able to learn that, to induce those features as part of learning. And specifically, we want to avoid the need to have data that's been annotated with those features. Traditionally, you need the data annotated with those features so that you can just apply supervised learning. But if we use latent variables, then we can induce those features automatically, and we don't need the annotated data. And graphical models are a principled way to define a probability model with latent variables. So in the last couple of years, there's been a lot of interest in latent variable for parsing because of these facts. All these models use, they start with a PCFG or something like that with a set of atomic categories for the labels, and they want to expand those categories to more detailed set of atomic categories. And until very recently, they've actually had a lot of difficulty getting very good results. And I think that that's basically because it's very hard to learn the latent variable annotations. It's a difficult search problem to learn those annotations. So they have some split merge techniques and hierarchical distribution processes that help them do that search. And that's why I think they've succeeded. We take an alternative approach where instead of having atomic categories, we have vectors of latent features. And I think that the reason that's so successful is because it gives us a richer similarity space in the latent variable annotations. You know, a given annotation has a lot of similar annotations just by flipping some bits.
Is the video not being
I think it's too small.
Yeah, the presentation button.
The red one on the
Not that one.
I think it's the green button.
Yeah.
No.
Right? There. No? Yeah.
Yes. Is that good? Thank you.
Okay.
Talk to you soon.
Right. Okay, so by searching in a feature space instead of searching in an atomic category space, the learning becomes easier. So it's my intuition as to why this is working so well. Okay, but as soon as we have vectors of features as our latent variables, then inference becomes intractable. So we need to start looking at approximation. So I'm proposing a graphical model which is specifically designed to make the approximation efficient. And I'll discuss two approximations. One's a feed-forward approximation. They're both mean field approximations. One is first is equivalent to the neural network I mentioned before, and the second one is a more complicated mean field approximation. So in order to argue that this graphical model is a good abstract model that we should be working with, first thing I need to show is that when you have a better approximation, you end up with a better parser. So that's what we'll look at in the evaluation section at the end, and also just that we end up with good absolute numbers. So it's worth continuing with. Okay, so now I'll introduce the different pieces that go into defining the graphical model, and then the specific architecture. So it's a Bayesian network, which means it's a directed graphical model. The nodes are variables. The links define conditional probability distributions, as probably most of you know. The probability distribution for a given variable is a parameterized function of the input variables values, and variables can be divided up into visible variables, the ones where we know their value, and hidden variables, the ones where we don't know their value, and we want to marginalize out those hidden variables. Okay, so sigmoid belief networks are a kind of Bayesian network where the activation functions, the probability distributions, are defined in terms of a sigmoid function, or in general, a log linear model. Could be a normalized exponential. And as I said, we're going to use vectors of binary latent variables for these hidden variables here. So the third component is dynamic Bayesian networks, which is a way to deal with unboundedly long sequences, because we're dealing with parses. Sentences can be arbitrarily long, parses can be arbitrarily large. We need that.
Excuse me, can you go back one slide? So is that the probability distribution here? Or,
Yeah.
value random variable, or what makes it?
Yeah. So so this would be the probability. Just these are actually normalized exponentials, but these are just binary random variables. And so the probability that the value of that variable is 1 is a function of the parent variables, which are these here. And it's just a weighted sum. They're weights on these edges. So a weighted sum of the input variables. And then this is a sigmoid function. And that gives you a probability between probability of being 1, which tells you the probability of being 0.
I see.
Okay, so Dynamic Bayesian networks for dealing with unbounded sequences. The typical example of a Dynamic Bayesian network is a hidden Markov model, where you have the Markov assumption every state is dependent only on its previous state or some bounded window previous states. Okay, but for our application, that's not appropriate because we're modeling derivation sequences. So every tree, for any tree, we can define a derivation for that tree. And then we modeled those sequence of derivation steps. So it's the actions that a parser does in constructing the tree. These sequences are not Markovian. Particularly neural network work has tried to pretend that it is Markovian, and it just doesn't work. The dependencies in the sequences, there are dependencies you need in the derivation sequences that can be reaching arbitrarily far back in the sequence. And that's because the locality, the appropriate locality, is in the output parse tree. If you want to know the probability of, say, a label of the tree, it generally is sufficient to just look at the local context in the tree. But that doesn't map to a local context in the derivation sequence. So we want to have some way to define our graphical model so that those links between variables represent locality in the tree and not locality in the sequence. So the method we use is the incremental specification of model structure. So the idea is you're proceeding through the derivation, and at this point we wanted to say estimate the probability of this variable here. These are all visible variables. We define this set of the statistical dependencies as a function of these visible variables. So it gives us a kind of switching model. We switch this structure of the model here depending on what the visible variables here are. That switching is done, the definition of these statistical dependencies is done based on structural locality in the partial structure that's been built up as defined by this set of decisions that you've already made.
So, sorry, just to clarify. So you're saying that basically if you want to build a parse tree, you're going to have some sequence of operations which are going to decompose the building of that parse tree.
Right.
And the dependencies that you would like to have for constraining the parse tree probability are not local in the sequence.
That's right.
Traversal order, right? That's
Correct.
the problem that we're looking at here.
That's right.
And how exactly are you addressing it?
By having this switching so that, say, this link can go arbitrarily far back to previous states. And as we'll see...
the states are in the sequence that I used to build the parser?
Right. The states are in the sequence of actions that the parser does, the derivation. And it could be that, say, you started out building a noun phrase, and then you went off and built a relative clause, and it took you a long time. And when you come back to, say, predict the verb of the sentence, you need to then be linking to a variable associated with the head noun, not with what's at the end of the relative clause. So you need that local relation. So it's very local relationship in the tree, but it can be arbitrarily far in the derivation sequence, because you've got that relative clause in between. So you need to have some way to define these long links, and they're defined by looking at that tree, that has structure of the tree that you've built with this sequence of actions.
But there's more than one way of decomposing the tree into a sequence of operations.
That's all your important design decisions in deciding how to use this framework, apply it to parsing.
So none of that, I mean, you assume that somehow you come up with a good way of...
Yeah. That's where the domain knowledge comes in.
I see. So that's left to the modeler.
Left to the modeler.
Once that is decided, you're going to use something like
right.
this to build the problem.
Right. So I don't assume a top-down derivation or anything like that. That's all left up to the modeler.
Okay, thanks.
Okay, so this is what we end up with then. A dynamic sigmoid belief network with incrementally specified model structure. And this is the detail. We have these vectors that are representing the state of the parse. We actually decompose our decisions into a sequence of decisions. And we have dependence on previous states, but also we allow dependence on previous visible variables, previous decisions, via some arbitrary function extracts features from those decisions, and those are explicitly input.
Question?
Yeah.
I'm not clear how this is different than from these models where you're just conditioning on a longer history. There are various models that are more
Well, there's no bounded window. There's no bounded window that you can use. It can be arbitrarily large. Okay? And also, just making bigger and bigger windows only works if you have more and more data, and then you're not imposing any linguistically appropriate bias if you just use bigger and bigger windows. It could be any kind of string, but you know that it's a parse, and so you want to encode that structural information in your statistical model, because otherwise your learning problem is just hopeless. Yeah.
What sorts of constraints are there on this structure? Is there some sort of constraint on how many events you can condition on when you add the long loops?
A bounded number.
Okay.
Arbitrary, but a bounded number. You need to have a fixed set, because you need to, for each relation, there's a set of weights, and you need to learn those set of weights, and you need a finite number of parameters. Okay, so this is the first slide about why did we choose, of all the different ways to define a graphical model, why did we choose this one? And it's so that we can do the approximation efficiently, in particular so that we can have lots of possible model structures without ever having to sum over all the possible model structures. We don't need to marginalize over the model structures. And that's for three reasons. One, because of the incremental specification model structure, it's only the future decisions that you don't know the model structure for yet. And all the unknown edges in this model structure are directed from the past or current structure to the future, and there are no visible variables in the future. You don't know anything about the future because it's a generative model. So given those three things, we can derive that those edges can have no effect on the probability that we want to compute, which is the probability of the next decision. So all that future model structure is just irrelevant. We can ignore it. We don't even have to think of what it looks like, and therefore we don't have to marginalize over that all possible model structures. Okay, so now I'll show how this can be applied to parsing, and then once we see that, we can talk about approximations. Okay, so as I mentioned, it's a history-based model. We're modeling trees as our isomorphic derivations, and then we're parameterizing that as a probability of the next decision conditioned on the history of previous decisions, just the chain rule. We also allow non-atomic decisions for our decisions. It could be a sequence or hierarchy of decisions. So what we want in the end is the sub-decisions conditioned on the history of previous decisions and previous sub-decisions. So we do that by, we estimate that probability by building the structure for the history plus the current decision. We only need this much of the structure, as I said, because the future structure is irrelevant. And then we do inference over this model. Okay, so one of the crucial features of this model, as I've mentioned, are these vectors of features that are representing a compressed representation of this unbounded history here. You can also think of it as a label of the state of the parser. But if we think of it as a compressed representation of the history, it's used for computing the output, but it's also used, say this one is then passed to a future compressed representation. So you can have a feature passing situation where you learn something that's relevant here, and that feature then gets passed to here, or maybe passed to here, to here. So you can have feature passing all through the network, through the sequence of latent variables completely induced during the course of learning. And if you design it right, you can end up with a model that has no hard independence assumptions, which is unique in parsing work. On the other hand, it does have soft independence assumptions. It has soft biases because the longer the chain of states it needs, the information needs to pass through, the more likely it's not going to be learned. So there's a strong locality bias. And so when you're designing this, what these links are going to be, what you're doing is designing that locality bias that's going to bias your learning to learning certain correlations and ignoring others. But it's a soft bias depending on locality and, as I said, locality in the structure. Okay, so as was mentioned, to build one of these models, we need to define a derivation order. So we use predictive LR derivation order, which is a kind of left corner derivation. And that's because of efficiency of the parsing. And the statistical dependencies, again, are designed by hand. And those are also taken from my earlier neural network work. Rather than going through those, I'll just give an example. We start out with a generic root node and predict the first word, project the next, project an NP, and at each step, we're building a new bit of the partial structure by, depending on the decisions we chose here. We're assigning the next state to one of the nodes. We assign it to the node that's on top of the parser's stack at that given time. And then we derive the set of links to previous states based on structural locality between the node on the top of the stack and the other nodes in the partial structure that's been built up so far. And then we want to do inference over this graph.
So you were saying before that the further structure later on is irrelevant. You're assuming.
Yeah. Well, I can show it. Yeah.
Right. So does that mean then, if you're doing this type of parsing scheme with the left corner, that it's kind of an incremental parsing scheme? You assume that you can get the best derivation without looking ahead?
You need to do search. I mean, it makes the decoding problem more complicated because you have to basically guess what the best derivation is going to be, keep a lot of them in parallel, and it's only when it comes to actually predicting that future word that you discover that some of those things were really bad and some of them were good. So that's true of all generative models. I'll talk about that at the end. So here's another example that might look a bit more familiar to people familiar with HMMs. It's dependency parsing, where we're just trying to recover these head-dependent relationships. We don't have internal structure. So again, we're assigning our states to the node that's on top of the stack at that particular time. There's also a node that's at the head of the queue. And the derivation order is defined in terms of previous work on dependency parsing. And then we defined the set of statistical dependencies based on the structure that's been built so far. And at each point, we're computing a new state, defining the set of dependencies based on the structure, and then predicting the next action of the dependency parser. Okay, so that's the inference. So the inference problem we need to do is that. We need to compute the probability of one of these things given all these visible variables. And that's a very complicated inference problem. So we need to do approximation. It's completely intractable to do exactly. Its sampling methods, if you tried to do them exactly, also would be too complex. We're looking at approximate sampling methods, which probably are also a good way to go. But so far, we've looked at mean field methods. So mean field methods, it's a variational method. So we have an approximate model that we define. In mean field, it's a fully factorized approximate model, which we choose because it can be easily computed. We can do inference in that model tractably. This model has a set of free parameters, namely the means of the variables in Q. And we want to set those means to minimize the Kubelik-Leibler distance between the approximate distribution and the true distribution. Okay, so that's the mean field approach. That's also too complicated because in general, every time you see a new visible variable, you need to update the means for the entire structure, which can be expensive. So the first approximation we look at is the most efficient possible one, namely every time, for every variable, you only compute its mean once. The first time you see it, the first time you need that variable to compute a probability, you estimate its mean, and then you never update it again. You continue to see more evidence about the parse, but you assume that it's irrelevant for that mean. This gives us a strictly feed-forward computation, which is very fast, and it turns out equivalent to a neural network, and specifically because of the way I've designed the graphical model, it turns out to be equivalent to the simple synchrony networks that I developed in my earlier work on neural network parsing. So that's the sense in which we can think of the neural network as an approximation to a graphical model with latent variables.
What are some examples of these means that you're estimating?
So each one of these variables has a mean associated. The Q distribution is just exactly like this, only without any links, where it's fully factorized. And each one of these has a mean. And so you're trying to adjust all these well, we're trying to adjust these means so that they maximize or minimize the difference between the resulting distribution here and what you would get if you had the true full model.
So are those discrete random variables?
Yeah, these are 0, 1 discrete random variables.
So when you say mean, you have a parameter characterizing that distribution,
Yeah.
and it's basically the expected value of that policy.
Yes, it's the expected value of that 0, 1 value. And that mean is the activation value of the neural network. It turns out to be equivalent to the activation value of the neural network. Right, so I was back here. Okay, so that's the feed-forward approximation. The problem with that approximation is that it doesn't do any backward reasoning or bottom-up reasoning. When we then observe the decision, the next decision in the parse, we should go back and update the means based on that observation, and we don't do that. So this is mostly the work of Ivan Titov, but we developed a method that does update these means, but only for the current step. We don't go back all the way through the parse. We only update the current set of states when we see a new piece of information about the derivation for this state. And that involves a numerical method that we run to convergence to minimize this Kublek-Leibler divergence. Okay, so the first question is, are these good approximations? So we did a simulation with just a sequence labeling problem, so it is a Markovian problem, and we did that because then we could do a Gibbs sampler to give us an upper bound on how good an approximation we could possibly expect. We use unigram as a lower bound, and the neural network has a 63% error reduction over the unigram. The incremental mean field has a 73%, and the incremental mean field has a 27% improvement over the neural network in error reduction. So incremental mean field is a better approximation than the neural network, but also the neural network is also a pretty good approximation.
So, I'm sorry, what are we looking at? What problem was this?
This is just artificially generated problems. So we took a Markovian version of this model. We randomly generated the parameters of the ISBN.
No, I mean, is this parsing part of speech tagging when you say
It's part of speech tagging. It's
part of
just a
speech tagging.
sequence labeling. I forget. We had a small number of labels, and define a model, generate a bunch of sequences. But then we verified that these two had a sufficiently different values so that we could get a meaningful result. Took those. I think we had 10 experiments and ran these on them. So it's completely artificial data, so we know what the abstract model is supposed to be doing, and we generate the data.
So you used a unigram model to do the generation of the
No, I think it's a bigram model
bigram on the tags?
on the vectors of tag features.
So it's a hidden Markov model?
Yeah, but with vectors of features. It's a hidden Markov, yeah. So this is a much simpler model than the parsing models, but we did that because then we could run the Gibbs sampler and get an upper bound. Okay, so incremental mean field is a better approximation in neural network, but they're both good approximations. Okay, so how does the neural network end up being at all reasonable as an approximation? So this is the second aspect of the model that makes it designed to be approximable. And that's these links here. If in a hidden Markov model, you wouldn't have these links. All the information about these variables would be passed through backward reasoning to these variables and forward reasoning to these variables. By adding these links, we're providing a shortcut. So with forward reasoning, we can compute an approximation to this chain of backward-forward reasoning. So that's why the neural network manages to do a reasonable job, even with just forward reasoning. So when training the parser, we train the approximate model. Both these approximations define perfectly good probability models, so we just train the approximate model. We don't try to find an abstract model directly. And that training just involves gradient descent, so it's backpropagation for the neural network. And for the mean field, we need to assume convergence of the numerical method and then solve some equations. Okay, so the last bit I need to tell you about is the decoding. As I mentioned before, we chose the derivation order so that we can parse efficiently. And specifically, it means that we can do beam search with a very small beam. So after every word prediction, which is where you get new information about the sentence, prune down to only 100, 20 or 40 still does very well possible derivations. And then there's also a branching factor limit just to keep the really bad cases from blowing up, but it doesn't have much of an impact. So we're doing a beam search through the space of possible parses. Okay, so evaluation, as I said, we have two questions. One, is it worth trying to come up with a better approximation? Will it give us a better parser? And two, are we getting good results in absolute terms? So we use a standard benchmark data set, but we're only looking at words, sentences at most 15 long. Several people have done this before. We do that basically because the mean field method is slow to train and we didn't have time to run a sufficient number of experiments. We're running this on the mean field, on the incremental mean field on the full data set now, but we don't have those results yet. So the results on that data set are that the incremental mean field does do significantly better than the neural network, almost a full percentage point, which is a lot for this task and these levels of performance. And therefore, we conclude that ISBNs are a good abstract model. They're something worth trying to approximate.
Did you run any of the standard parsers on your training data set?
So these are the results from previous papers on the exact same data set. So training and testing on sentence most 15 words. The IMF is not statistically distinguishable from the best results on this data set. Okay, so that answers our second question. In absolute terms, we are getting good results. So again, it's worth pursuing this approach. Okay, so but that's the 15 words data set. So I wanted to look at I wanted to show you the results on the standard complete data set. These are the results of generative models on this data set, where we're very close to the best results with our generative model, even though that we have a fairly small vocabulary. I think I can get better results because this is done with an external tagger. If I incorporate the tagger into the probability model, I get a better results on the validation set. But I haven't run that. I haven't written it up, so I haven't run it on the test set yet. And I think it'll probably be around the same, if not better, than the best result there. In terms of latent variable models that have been run on this test set, we get the best result. This is not the generative model I've been talking about. That's a little bit worse than the Berkeley people, but this is the same model that's been trained based on a discriminative criterion that I'll talk about in a minute. So that's the best latent variable models. These, so this is basically the best results from all the different groups that have run experiments on the benchmark data set. Again, we're one of the best. See, there's this whole 89 to 90 group where we're on either end of that. And then a couple little better than 90, but one of the best. And this is a much bigger and much slower model. They're both much slower in terms of parsing speed. Okay, another set of results. This is from this year's Connell shared task on dependency parsing. We just sat down, designed a model, implemented it, ran it on the data they gave us for the task, and we end up with the third best result. This is the average result across all 23 systems that were submitted, and very close to the best result for the task. And there were only two better models, and those were both multi-version systems. They were combinations of multiple models, which you can always get improvement by combining multiple models. So we were the best single model system. So in that sense, we have the best dependency parse, single model dependency parse. So this is a graph of parsing times for the dependency parser. To get the accuracy, we're running way out here somewhere to get the absolute best accuracy, but you see it really flattens off. So with just a small decrease in performance, you can get a much faster parser just by searching with a smaller beam width. So we're getting 60 words a second for 1% decrease from the maximum. And so that's, as far as I'm aware, much faster than other dependency parsers. This is for this sample of languages.
So did you measure the search errors? Like, are the remaining errors search problems or modeling problems?
Well, this difference, up here, there's no search problems left because you're really flattened out. Well, otherwise, increasing the beam would improve the performance, and it doesn't. You can increase the beam as long as you want, and it just doesn't make any difference. So at least they're not random search problems. Maybe some systematic search problem, but I really doubt that. Okay, so I mentioned those discriminatively trained version of the model, so I wanted to talk about that. Well, I guess I've had some questions during the talk, so I can go over my 45 minutes. So instead of optimizing this generative joint probability, we normalize out we normalize it so that we get a conditional probability. But this involves, and then we try to maximize that objective function. Problem is that then we have to sum over all possible parses. At testing time, we actually use this model as a re-ranker over the generative model. Those are the results I've showed before, and that's because of the way we train it. Instead of summing over all possible parses, we sum over the most probable parses as determined by the generative model. But it's not just a simple re-ranking model. If you just sum over the candidate parses and normalize like that, it doesn't learn very well at all. Instead, I have a method where the pruned derivations, their probabilities get approximated. So you can think, so the set of possible derivations forms a tree, and you have some subset of that tree in your candidate set. And there are places where the possible derivations have been pruned off by the search. And if you approximate so the conditional probability ends up, you're looking at the forward probability and comparing it to the backward, the sum of the backward probabilities. If you approximate the backward probabilities for the pruned searches, pruned derivations in such a way as to minimize the difference between the discriminative and generative objective functions, then you get the result that I showed before. You get this very good result. So it's a way of doing discriminative training. Yeah?
How much benefit do you think is coming from the fact you're using this way to find these really negative examples as opposed to simply just doing re-ranking? So in your discriminant criteria, right?
Yeah.
So the typical re-ranking method just use a Kenda and Bacillus, for example.
Right.
But you've taken it a step further and you're finding particularly bad negative examples to discriminate against, right, in that conditional model.
I don't know if I'd put it that way. Well, I can tell you that for the data-defined kernels, we did a re-ranker version of the data-defined kernel and trained I think we did a voted perceptron. And we got almost as big an improvement. But that's a large margin a method which generally produces better results than just a conditionally trained method. The conditional training, what it does is basically, in the generative model, you have to learn all these word predictions. And you're trying to actually learn what is the next word going to be. And that's a hard thing to learn. With the discriminatively trained model, all you're trying to learn is, given my history, if this is the next word, is that evidence that I'm wrong? Or is it evidence that I'm right? And that's a much easier thing to learn. So you're basically just learning to check whether your derivation is consistent with the word. And that's where you get the advantage here. So it's a simpler problem. Okay, very briefly, because I know people here are interested in speed, and because of the question about the search of the generative model, I defined a different probability model that includes the conditioning on the lookahead string. So the probabilities that you're using to search with are actually using that lookahead string. And therefore, the pruning is conditioned on what you're going to see in the future. Problem is, it's very difficult to condition on an unstructured string, even though I'm using a neural network run backward over the string. So there isn't actually a window effect, but there's a kind of soft window effect. Anyways, the absolute performance is lower than the generative model because it's very hard to condition on that future string. But as we see, we can get away with a much smaller beam. This is, I think, 2, 3, beam width of only 2, 3, 4, 5. So very small beams that you can then search with. So the natural thing to try is, what if we prune with the lookahead model and then re-rank with the generative model. And then we get this nice curve here that smooths out between the two curves. So we can get good performance even if in this region where we're running fast. So these absolute numbers aren't appropriate. I ran these experiments a long time ago, but that's the kind of curve you get if you do pruning the search with a lookahead model, and then you actually choose the best parse with the more accurate generative model. Okay, so conclusion. As I said, ISBNs are a good abstract model. They provide a powerful method of feature induction. We can approximate ISBNs in a tractable and effective way. Even when we use a very fast approximation, it's still very effective for parsing. And not surprisingly, discriminative methods give us an improvement over the generative methods. So that justifies looking at more accurate or more efficient approximations to ISBNs, using this as a framework for formalizing how to improve these models. Specifically, I'm interested in looking at regularization. We should be able to have a regularizer such that when we learn, we're learning a model that can be effectively approximated, accurately approximated. And it turns out that standard weight decay Gaussian normalization on the neural network does minimize a bound on the approximation error, but we can come up with better bounds. So it's a very interesting way to justify regularization. And then, of course, there are other things we could apply this architecture to, not just parsing. Paula Merlo is working on semantic parsing. I'm collaborating with her on that. We could also do synchronous parsing for SMT, or if anybody's got a problem, I'd be interested to hear about it. Thank you.
I think we have more time for questions. We started a little bit late.
How big of a difference does it make on the choice of sigma as the distribution of higher unobserved?
Sigmoid versus what?
I don't know. Did you consider sigmoid?
It's just what you get if you have a log linear model, and everybody uses log linear models. I don't really have a better answer than that. It's smooth, it's easily differentiable. Yeah.
Can you say something about the elementary parametric set of the parsing model? What I mean, it was there in some of the slides, but it wasn't clear.
So the parameter set is for the model, for the slides that had, well, maybe it's, okay, so this has the individual links, and each one of these links has a weight, and that's the set of parameters. And each one of these has a bias.
But in terms of the actual lexicalized, this is a lexicalized parsing.
Yeah.
So,
Okay. We have, for the best results, the vocabulary size is about 4,000 tag word pairs, and anything else is treated as tag unknown word. There are, in Penn Tree Bank, I think 36 non-terminal labels you need to predict. Yeah, that's it. It's just a structure, the labels and the words. So that's what goes. These sequence of decisions down here are things like, okay, first we decide to project a new node, and then we decide to choose the label of that node. So that's the sequence of subdecisions.
With respect to your ability to handle these long-distance dependencies, do you expect that when you're in mean field tests are done full data for long distances, to see an even greater divergence between the results and previous work?
Well, the mean field is itself incremental, so we don't actually update the means for the more distant things. We only update the means for the current state. So I guess you might just, yeah, I guess you would. You would because you have a more accurate estimate of those means. It not only gives you more accurate estimates now, it gives you more accurate estimates in the future. The future states that then condition on this state are getting more information out of those hidden units. So I would expect it to be better at passing features around long. We had some results, particularly for the dependency parsing, that our method compared to other methods is actually very good well, relatively good at just outputting the long distance dependencies in the dependency structure. And I think that's largely because of this ability to pass features. Yeah.
So I have two questions. One, if you look at your model, as you said, you have a sequence of predictions that you need to make. And if you define each of those as an event, how many such events, and then in your training data, and then how many parameters do you end up with in the model after training your model?
The events in the training data, the training set is just under 1 million words, I think, and the number of events per word is, I think it's under 2, so maybe around 2 events per word.
1 to 1 million
Yeah. Events in the training data. And the number of parameters, I have 80 hidden units, so there's 80 squared of these parameters. Small number of structural decisions. There are a huge number of parameters in the word prediction, because you have 4,000 possible tag word pairs you can predict, and that times 80. So there's a huge number of parameters there, but they only get, well, they're either not used very often. For the numerator, they're not used very often. For the denominator, they do get used because you need to normalize over the set of words, or set of words for a given tag. So they're not so crucial. There's a huge number of them, but they're not so crucial.
So we're looking at, you said 4,000 times 80, that's roughly 300,000.
Yeah.
For 1 million or so events.
Yeah.
So you'd end up with maybe 10 samples per rough.
Well, it's not quite so simple, because every param, except for the word predictions, virtually every parameter sees virtually every event.
Wow. Great. I don't know.
And it's regularized, so it just stays near 0 if you don't have enough data. It just stays near 0 or goes to 0.
And my second question was more general. I'm sure you've got this somewhere else. I mean, do you see parsing as a problem in itself, or you would like to use this to solve other problems?
Well, I think parsing now in NLP has become a benchmark task for structure prediction problems, in machine learning applications to structure prediction problems. People aren't so much just trying to get a better parser. If I was doing that, I would do something like Charnack and Johnson, have a huge number of features to a max end, SVMs, et cetera, throw everything you can think of, have 20 different models, et cetera. Then you'd get a better parser, you'd have the best parser in the world. Nobody really cares. You want to run an experiment where you have you have a method, you want to see if it works, you do a controlled experiment. So that's really what people are using parsing for now. But that's just kind of from the people interested in structure prediction problems. Otherwise, I think parsing doesn't have a great history in improving people's applications, but I think the time will come when it will. We're kind of running out of what we can think of for n-gram models, in my opinion. And the fact is, language has these very clear structural statistical dependencies, and if you can somehow exploit that information in a robust statistical system that's tailored to your particular application, then I think we will get quite big improvements in the not too distant future.
So you're interested in for the machine learning aspects of parsing.
That's what I've done in the
Express
past. That's what I've done in the past, but I would be interested in the more application side. There's a lot of interesting problems in how to integrate tasks, and I mean, it's not enough to just come up with a parse and pass that one parse to the task. That's certainly not enough.
All right, that's a good way to end.